Welcome back to Integral Calculus. In this video, we're going to be talking about integrals involving secants and tangents. Much like with the integrals involving sines and cosines, the idea here is that as things get messy, we can rewrite them in a way that will simplify things. Well, you've learned in your previous study of trigonometry that given any kind of expression involving trigonometric functions, you can always rewrite it as an expression involving just sine and cosine. And sometimes that will be the right choice. Take whatever you have and rewrite it in terms of sine and cosine and hope that you can go from there. But it's worth knowing a couple of rules that you can use to sometimes use secant and tangent to your advantage. These rules are a little bit trickier than the sine and cosine rules because, well, the derivatives of secant and tangent are a little bit trickier. Remember that the derivative of tangent of x is secant squared x, and the derivative of secant of x is secant of x times tangent of x. So, when we are trying to rewrite things, we're looking for a leftover factor of secant squared, or a leftover factor of secant times tangent. If your powers on both secant and tangent are even, then this is fairly straightforward. If your powers on both are odd, then this is fairly straightforward. But in other cases, that's where things get a little bit tricky, and there's not a definitive you can do this. But let's go ahead and start off with this one. The integral of secant to the sixth x dx. I am going to immediately rearrange this and call it the integral of secant to the fourth x times secant squared x dx. I am really hoping that I can let u equal tangent of x so that du is secant squared x dx, and then this will be fairly straightforward. Unfortunately, that's not what I have right now, but if I take some time and do some creative rearranging, I should be able to get there. I will need to use the Pythagorean identity. If the only one you remember is that sine squared x plus cosine squared x is equal to 1, notice that if you divide both sides of this equation by cosine squared of x, you'll get sine over cosine squared plus 1 equals 1 over cosine squared. Sine over cosine is tangent, and 1 over cosine is secant. So tangent squared x plus 1 is equal to secant is the Pythagorean identity relating secants and tangents. We'll use that right here, and I'll rewrite secant x to the fourth as secant squared x squared and then that is tangent squared x plus 1 squared times secant squared x dx. And I could continue rearranging from here, it absolutely works, but at this point I'm going to go ahead and do my u substitution so that I have u squared plus 1, the whole thing squared, du. Now I'll multiply it out because it will be a lot simpler to do so. This is u to the fourth plus 2u squared plus 1. And when I integrate that, I get 1/5 u to the fifth plus 2/3 u cubed plus u plus our arbitrary constant. But of course, remember that u was tangent of x, so I can substitute that back in. I'll get 1/5 tangent to the fifth of x plus 2/3 tangent cubed of x plus tangent of x plus our arbitrary constant of integration c. Another example here, if I look at secant to the sixth of x times tangent of x dx, well, in this case, I notice that odd power of tangent. So my immediate thought in this case is, well, what if I rearrange this as secant to the fifth of x times secant x tangent x dx? And by arranging it this way, I'm hoping that I can let u equals secant of x, in which case du is secant x tangent x dx. And in fact, I can do just that without having to do any further thought whatsoever. And this one turned out to be a lot easier than the last one. Something that you may have thought of here. I could have separated this out, saved the secant squared x, and rewritten it as secant to the fourth times tangent times secant squared x dx, and done a u substitution, u equals tangent of x. I would have ended up with something that looked a lot more like what I got in the last example. And that actually does work. With secants and tangents, there are times when either approach is perfectly valid, and this is one of them. That can get to be really confusing because, oh, I got 1/6 secant to the sixth. I might have instead gotten 1/6 tangent to the sixth plus 1/2 tangent to the fourth plus 1/2 tangent squared if I had done it the other way instead. And those are not clearly the same thing. But if you use the Pythagorean identity, you can get from one to the other. It makes checking your work and comparing answers with other people a little bit challenging. Just because you use two different approaches, you might get two very different looking expressions, but that might not mean that they are different expressions. The trick that I use at this point, when things get this complicated, is to go to a graph. Go to Desmos or something like that. Graph each of the two functions. And if the graphs line up with each other, they're the same function. If the graphs are drastically different at one point, then something is wrong. It's not perfect, but it's a nice rule of thumb, and it's a much faster way of double checking yourself than trying to go through and do all of the algebra. All right. I have one other example that I wanted to look at here. Although before that, I do want to remind you, if you go back and look at a previous video, we looked at an example of the integral of secant cubed x dx. We wrote it as the integral of secant x times secant squared x dx, and we integrated by parts. You can do the same thing for the integral of secant to the fifth or any odd power of secant. It's not fun, but we've done it before. I don't feel like I need to do it again. The only other special case is, well, what if you only have tangent? The integral of tangent to the fourth of x. The powers that I'm looking for are secant squared or secant times tangent. And I don't have either of those right now. But I can always use a Pythagorean identity to rewrite this in terms of secants instead of tangents. And if I expand that out, well, the integral of secant to the fourth x is going to be a little bit annoying, but the other ones are pretty easy. I will point out here, there is no tangent in that second integral, but I'm still going to let u equal the tangent of x, so that du is equal to secant squared x dx. And then in the first integral, I'm going to rewrite that as the integral of secant squared x squared. And I'm sorry, that's not what I wanted to write. I'm going to write it as secant squared x times secant squared x. Right? They are the same thing, but this is the version that I wanted, because now I have a secant squared x dx that I can use for a u substitution, and I have a secant squared that I can rewrite using the Pythagorean identity. So I've got the integral of tangent squared x plus 1 times secant squared x dx minus 2 integral du minus integral dx. And I guess I can do the same u substitution over here. This will be the integral of u squared plus 1 du which integrates to 1/3 u cubed plus u. And then substituting back in, u is tangent, so this is 1/3 tangent cubed of x. And then I've got plus u minus 2u, which is all told minus u, or just minus tangent x, and minus x, and plus our constant of integration. I think I had said that that was going to be the last example, and it is, but I'm going to go through that same example again. If I come back up to where I wrote it down in the first place, this was tangent to the fourth of x. One of the things that I mentioned early in this video is that replacing things in terms of sine and cosine is always a valid choice. Although this one is probably going to be very unpleasant to try. You've got sine and cosine both raised to an even power. I guess the first thing that I would do here is rewrite the sign in the numerator as 1 minus cosine squared squared. Although I'm really not sure how I would approach it from here, because I will end up with a dx over cosine to the 4th x and some other stuff. And I think the only way to get anywhere from there is to rewrite it as secant, which takes us right back to where we started. So that non-example, I hope, gives you some indication as to why it's worth knowing these processes. If you have a factor of secant times tangent that you can bring out, and you can get everything else in terms of either, or I'm sorry, and then you can get everything else in terms of secant because you have tangent to an even power left over, that works out nicely. If you can get everything in terms of secant squareds, that tends to work out nicely. If you end up with something that's a little bit more annoying, then, well, it's going to be a little bit more annoying. If you can't find anything else, rewriting things in terms of sine and cosine is a method of last resort, and it is that because really it's just doing the same things over again. All right. And if I can get my pen working, I'll wrap up here with one for you to try. A little bit more convoluted than things we've looked at previously, but the same rules are still going to hold. You've got tangent raised to an odd power, and you would really like to get rid of the secant. It would be really great if you could let u equal secant x in this case. With that hint, take a couple of minutes to play around with that, see what you can do with it, and I'll see you in the next video.